Good evening, Chem kids. I'm here to show you how to do an empirical formula problem and a molecular formula problem. We're going to choose one from the mole packet. So I chose from section 10.3, number 13. And we're going to do number 13, which is to find the empirical formula of a compound given that the compound is found to be 47.9% zinc and 52.1% chlorine by mass. The first thing to realize is that this is an empirical formula problem. So this is our keyword here. And the other important thing to realize is that they've given us percents. And so our rule is that when we do an empirical formula and they give us percents, we have to change the percents into grams. And we do that by assuming a 100-gram sample. And that's very clever because if you assume 100 grams, then 47.9% zinc becomes 47.9 grams of zinc. And 52.1% of chlorine becomes 52.1 grams of chlorine in a 100-gram sample. So the very first thing that we're going to do is we are going to change the grams of zinc into moles of zinc and the grams of chlorine into moles of chlorine. I'm going to move this out of the way. A little bit. So we're going to begin by converting 47.9 grams of zinc to moles of zinc. I'm going to go to the periodic table and find that zinc weighs 65.38, which I'm going to report as 65.4 grams of zinc. And taking out my trusty calculator, I'm going to divide 47.9 by 65.4. The sig figs are going to be 3 sig figs because of the 47.9, which is the given. And I'm going to get 0.732 moles of zinc. I'm going to do the same thing with my next element, which is chlorine. And I'm going to convert 52.1 grams of chlorine into moles of chlorine. 1 mole of chlorine from the periodic table is 35.5 grams of chlorine. Again, note that chlorine is not a diatomic element in this case because we're trying to find the chlorine in a compound and not by itself. 52.1 divided by 35.5 to 3 sig figs is 1.47 moles of chlorine. I'm now going to do the most important step, which is to divide by the smallest amount of moles, and that is 0.732. And we're doing that because these two numbers, 1.47 and 0.732, really have a relationship. They really are whole number multiples of each other, even though we can't see that yet. When we divide by the smallest, we get to see what's really going on. 0.732 is a whole number multiple of itself, and 1.47 divided by 0.732 gives us a whole number relationship of 2. At this point, we want the whole number. We don't want sig figs. We just want to know how these two numbers have a relationship to one another, and it's always going to be a whole number type of a relationship because that's how it works with compounds. Once I know that, then I basically have my answer, which is that in this compound, there is 1 zinc and 2 chlorines. And I'm going to write that 2 as a subscript. And therefore, my empirical formula is ZnCl2. Again, to review the most important steps. if you're given percents, assume a 100-gram sample. Turn the grams into moles. Divide by the smallest number of moles. Get your ratio, and then finally turn your ratio into a formula. If for some reason your ratios turn out to end in 0.5, in exactly 0.5, multiply everything by 2. So don't round down or round up, just keep it at 0.5 and then multiply everything by 2 to get rid of the 0.5, just like we did when we balanced equations. If you're given a problem where they already give you grams and not percents, you don't have to assume a 100-gram sample. You can go right into converting grams into moles and dividing by the smallest number of moles. We are now going to do a different kind of problem. We are going to do a molecular formula problem. Our keyword is molecular formula. Notice that they will always tell you that, and they will also always give you the molar mass. That is a huge keyword for us. And the molar mass in the case of a molecular formula problem is the mass of the parent. So the molar mass equals the mass of the parent formula. And remember what that means. An empirical formula is always, by definition, going to be a subset of a bigger parent molecular formula. The parent molecular formula could be a multiple of 1 or 2 or 3 of the empirical. In other words, the empirical formula will always fit a whole number of times perfectly into the molecular molar mass. And that's what we're trying to find here. We're going to first have to try to find the empirical formula for this problem, and then use the empirical formula to find the molecular formula. So let's get started. I'm starting with 56.36 grams of oxygen. And again, oxygen is not diatomic in this case because we're finding it as part of a compound. I'm going to turn that into moles. 1 mole oxygen weighs 16 grams oxygen. I have 4 sig figs here because my given is 56.36. That's 4 significant figures. 56.36 divided by 16 is, to 3 sig figs, 3.523. Next, I'm going to go for phosphorus. Phosphorus is 43.64 grams of phosphorus P. 1 mole phosphorus from the periodic table weighs 31.0 grams phosphorus. Don't forget to cancel the units as you go along. Again, I need 4 significant figures. That's my given. And 43.64 divided by 31.0 to 4 sig figs is 1.408. Again, we're finding an empirical first, so the most important thing here, since everything's in moles, is to divide by the smallest amount of moles to see what the whole number ratio is between these two numbers. So in other words, 3.523 and 1.408 are really related a whole number of times to one another, but we can't see that yet until we divide by the smallest. And of course, 1.408 divided by itself gives us a ratio of 1. And 3.523 divided by 1.408 gives us, 2.5. So this is one of those scenarios with the 0.5. I am neither going to round up or down with the 0.5. What I am going to do is I'm going to multiply everything by 2. So I'm going to get a ratio of 5 to 2. I'm going to use that 5 to 2 to get the empirical formula, which is P2O5. Notice that the 2 went with the phosphorus and the 5 went with the oxygen. The reason I wrote it that way, even though in the problem they gave us the O first, is because we want to try to write formulas from left to right, from least electronegative to most electronegative. And if you can't remember that, just remember that the periodic table is read from left to right, and phosphorus is further to the left than oxygen. If you had written O5P2, that wouldn't be the worst thing in the world. I would have accepted that as an answer as well. But let's try to do everything as correctly as we can. The next step, though, what makes a molecular problem different from an empirical one is the following step right here. To get the molecular, and remember, this is the empirical, so up to now it was exactly the same as the last problem that we did. We are going to take the molar mass, so add up the molar mass of the empirical, of this little empirical formula that we found. So that's going to be P2O5, that's 2 P's, so 2 times 31, and oxygen is 5 times 16. 2 times 31 is 62, and 16 times 5 is 80, for a total weight of 142 grams. This is the mass, okay? It's important to realize what this is. This is the molar mass of the empirical formula. Okay, our next step is to look at the problem and to realize that they gave us 283.9 grams per mole as the molar mass of the parent. Well, this empirical formula came from a bigger type of molecule that we call the parent. So this P2O5 is going to fit some whole number amount of times into this number 283.9. Okay, so the parent formula is 283.9 grams per mole. So we want to see how many times the empirical formula fits into the molar mass of the parent formula. Right? The parent weighs 283.9 and the empirical weighs 142.0. When we divide these two numbers, 283.9 divided by 142, we get a ratio of 1.99999, which is a ratio of 2. And what that means is that the parent formula is made up of 2 sets of empirical formulas, of 2 empiricals. And because the empirical formula was P2O5, since this was the empirical, then the parent is P2O5 times 2, or P4O10. So, to summarize, a molecular formula is done much the same way as an empirical formula. You start off by converting the grams into moles and getting the ratio of the numbers. And so your empirical formula is P2O5, so you have to do a molecular formula by first finding an empirical formula. If the problem happens to give you the empirical already, that's great, you don't have to do that, but sometimes you have to get your own empirical first. Then the key is that you add up the molar mass of the empirical, which we added up to be 142.0, and then we divide that into the molar mass of the parent formula that they gave you in the problem. In the problem, they're going to call that the molar mass. So look up here, the molar mass of the compound. That means that that is the parent. That is the parent. So you divide the parent by the empirical to find out how many times the empirical fits into the parent. In this case, it was 2. And since the answer was 2, we multiply our empirical by 2. And we get a final formula of P4O10. All right, Chem Kids, I hope this helped. I'm available by email. and I will see you tomorrow.